Hello and welcome to Dr. T's Algebra 2. In this lesson, I'm going to talk about some basics of complex numbers. And we're going to start with the imaginary number I. I is the square root of -1. And in a previous video, I talked about the idea that it could, in fact, drive a person mad thinking too much about what that means if there's an imaginary number. And so the simplest way to just think about that without going into too much detail, as there are some fairly mind-blowing concepts involved in this. When we see a negative number inside the square root, just pull that out. I tells us it's a negative number, and now we've just got the square root of whatever that absolute value is. The square root of 1 is 1, and so we got I squared. I behaves differently than regular square roots. Well, sort of. If I is the square root of -1, then I squared is the square root of -1 times the square root of -1. Any number in a square root multiplied by that same number in the square root is the same as if we had exponents of 1/2. And when we multiply like bases, we just add the exponents. So this is -1 raised to the power of 1/2 plus 1/2, or -1. Any square root times itself is that number inside the square root sign. Same goes for I cubed is the square root of -1 times the square root of -1 times the square root of -1. And as we already demonstrated, square root of -1 squared is -1. And so this is equal to -1 times the square root of -1. Or the negative square root of -1. And then the square root of -1 is I. And so this is all equal to -I. So what we see here is that odd exponent values for I come back imaginary numbers. And then I'll show you here, even exponent values of I are going to come back real numbers. Square root of -1 times the square root of -1 times the square root of -1 times the square root of -1. This is -1 times -1. Negative times a negative is a positive. This equals 1. And that cycle continues over and over and over. Even powers of I are real numbers. Odd powers of I are imaginary numbers. And so I by itself is something of a confusing point, but we see it in complex numbers. We see it with the quadratic formula, and then we'll see it with rational expressions like 3 plus 6i over 4 minus 2i. Well, sometimes we like to rationalize the denominator, get a rational number on the bottom. Or if we have a complex number on the bottom, it's easiest to work with if we can make that denominator a real number. So what we're going to do is multiply by the complex conjugate, which in this case is 4 plus 2i. It's whatever this thing is on the bottom, we're just going to change the sign there. Change that sign in the middle. And so we're going to end up with a difference of squares. If you recall, a difference of squares looks like x squared minus a squared, which is equal to, in factored form, x plus a and x minus a. And so again, we've got some kind of a rational expression with complex numbers on the top and bottom. We're going to multiply that by the complex conjugate so that we can get a real number on the bottom. And when we multiply by something over itself, this is just like multiplying by 1. It doesn't change the actual value of the equation. It's just like multiplying by 1. And then we can expand these two binomials just the same as we would. That's just distribution. by distributing the first part of the first set of parentheses by each part of the second, and the second part of that first binomial by times each part of the second. Just distribution. So we got 3 times 4 plus 3 times 2i plus 6i times 4 plus 6i times 2i. And that's all going to be over. Well, we already know this is a difference of squares. This is going to be 4 times 4 plus 4 times 2i minus 4 times 2i, and these two will cancel out. And then at the end, minus 2i times 2i. Carry out the operations on the top and bottom, and we get 12 plus 30i, that's this 24 here, 6 times 4. We can multiply the real part, the integer there before I, and any other integer. So we're multiplying 3 and 2, which is 6, 6 and 4, which is 24. We get 12 plus 30i, tack the I on the bottom, on the end of that, and then plus 12i squared. When we multiply 6 times 2, we also need to multiply I times I, and we get 12i squared. And thinking back to the table, I equals square root of negative 1 equals I. I squared equals negative 1. I cubed equals negative I. I to the fourth equals 1. And that cycle repeats over and over and over. On the bottom here, we've got 16, which is 4 times 4, minus 2 times 2, which is 4, I times I is I squared. Now we can substitute for I squared. This is actually negative 1, this is actually negative 1. So we're going to have 12 minus 12, which is 0. So on the top, we're going to get 30i alone. And on the bottom, we've got 16 minus negative 4, so 16 plus 4, or 30i over 20. And we can still factor out a 10 there. We've got a common factor, so we're going to get 3i over 2, or 3 halves I, or 1.5i. Now looking back at I briefly, I stopped at I to the fourth, but if you should have, for example, I to the 63rd, we're just going to take 63 divided by 4, and we'll get 25 as the nearest value. Sorry, 15 is the nearest value. And that's going to be 15.75. 15.75. That 0.75 means it's I cubed, right? For each 0.25, we're going to add 1 to the exponent. So if we get a real high exponent value, if we get a remainder of 0, then we're going to have I to the fourth, right? So 15.75 means 15 remainder 3. If you get a remainder of 1, then that's going to be I to the first, or I. Remainder 2, I squared, and remainder 3 is going to be I cubed. All right, so for each the remainder there, when we divide by 4, for 1, 2, and 3, will tell us the exponent, and if it's a remainder of 0, that means it's I to the fourth, or 1. And so again, I recommend not thinking too deeply unless you are a future doctor of mathematics. Even in that case, I think this is a mind bender that could send people down a rabbit hole that is not entirely productive. So my advice is take I and imaginary numbers at face value. Just recognize that I only means that there's a negative number inside of the square root, and then try to memorize these basic progressions of I. So we multiplied by the complex conjugate, which gave us a difference of squares, and then simplify by taking out common factors of the numerator and the denominator. These still work like regular fractions. Rational expression works as fraction. Rational expressions work as fractions, and we'll see more of these in a future video. Okay, this is Dr. T's Algebra 2. Thank you.